the directional derivative. Just like in the previous video, let me start things off with a picture to motivate what's going on here. So now I want to think of, this is a contour map of some mountain here. So this is some ridge right here. This is the top of the mountain. This is the plain around the mountain kind of thing. And let's assume that you are at this point here. Call this point P. What meaning, let's just remember, what meaning do the partial derivatives have? So the partial f, partial x, this is the rate of change in the x direction. So if we are moving in the x direction here, if we're at point P and walking in the positive x direction, this gives us the rate of change. So we can see here that we are going up the hill. So the rate of change here would be positive. It would be, but it's not the most direct way to get up the hill. Partial f, partial y. This is the rate of change in the y direction. So, okay, let's say you want to move in this direction. This is the y direction. You're moving down the hill pretty quickly here if you go in the y direction. This is the meaning, this is the geometric meaning of partial f, partial y. So these two partial derivatives give us information about changing in either the x direction or the y direction. But what happens if instead of going in either one of these directions, we want to go like in this direction? So what about the rate of change in the direction of u? What can we say here about this direction? What can we say here about this rate of change? It's not the rate of change in the x direction, it's not the rate of change in the y direction, but we sure would like to have information about the rate of change when we go in this direction, this direction, this direction, or any direction we might want. So the heading here, the directional derivative is the computational tool that will allow us to figure out the rate of change in any direction, not just x direction or y direction or z direction if we have three variables, but in any direction. So here is our definition. If u is a unit vector, the directional derivative in the direction of u is the directional derivative of f in the direction of u, evaluated at a point P, is you take the gradient, you evaluate take the gradient f, evaluate it at the point P, and take the dot product of it with u. And so I'll just, let me highlight two things here. So first is that u has to be a unit vector. So the directional derivative is defined in such a way that u is a unit vector. If u is not a unit vector, if you don't have a unit vector, scale. So you just have to scale it. You have to take your vector and find a unit vector that's pointing in the same direction before you apply this formula. And then I won't go through the details here, but I'll just say that a proof of this is a special case of the chain rule for paths. And we can kind of see that it's see that this looks familiar. The fact that this is a gradient evaluated point dot product with some other vector. This is very evocative of the chain rule for paths. Okay, so let's go ahead and apply this definition here. So suppose that f of xy is x squared y cubed. V is the vector 1, 1, and we want to do this at the point -2, 1. We want to find the directional derivative of f in the direction of v. So what things do we have to do first? Well, the first thing that maybe we should note here is that we need to scale. So v, the magnitude of v is equal to square root 2 here. Square root of 1 squared plus 1 squared is square root 2. So instead of working with v here, u is going, let's have u be a unit vector in the direction of v. U will be 1 over square root 2, comma 1 over square root 2. This is a very common thing that people forget, so I want to highlight this right here so that you don't forget this. Okay, what else do we have to do computationally? So we have the u vector, now we need the gradient. So the gradient of f is, okay, so the partial derivative of this with respect to x is 2xy cubed. The partial derivative of this with respect to y is 3x squared y squared. And we see here, now let's go ahead and plug in our point P. X is -2, y is 1. And so x is -2, we get -4, comma, when x is, so 2 times -2 times 1 cubed is -4. 3 times 2 squared is 12 times 1. So the gradient evaluated at P is -4, 12. Okay, so to finish this off, du f of P is equal to -4 comma 12 dot product with 1 over square root 2, 1 over square root 2, -4 over square root 2 plus 12 over square root 2 is 8 over square root 2 is 4 times square root 2. So this is our final answer. And to wrap up the discussion of this particular problem here, let me point out that if f corresponds to height, then the rate of change, this is the rate of change in height as you move in the u direction at P. So I know this got a little bit scrambled here, but the idea, I mean, this is not the right drawing. This drawing does not correspond to this function, but the idea here is that, like, at point P, this point P, if you go in a certain direction, u direction is this right here, this is your change of height. So in particular, note that you're going uphill. 4 square root 2 is positive, so you are going uphill. If we had obtained a negative answer, we would have been going down the hill. Okay, to wrap up this video, one more comment just to make here is that suppose we use u is equal to I hat, so the unit vector, the standard basics vector in the x direction. What happens is that, okay, so and let's assume that we're working in 3 dimensions right now. So the gradient of f would be partial f partial x, partial f partial y, partial f partial z, dot product with I hat. Of course, I hat is just the vector 1, 0, 0. This chooses out the first entry here. So so this would be, what's the, if we have I hat as a unit vector, the directional derivative in the direction of I hat is just the partial derivative with respect to x. Similarly, the directional derivative in the direction of j hat would be the partial derivative with respect to y, and ditto for k hat and partial derivative with respect to z.